of the atom was something called the plum pudding, believe it or not. And that is, J.K. Thomson described the atom as having particles in it. So in the quest for what is everything made up of and the description of the atom, they had all kinds of particles, but they had no specific order. And he says that the electrons are scattered like, now this is the part where it gets weird, like raisins in a plum pudding. So you have to know what a plum pudding is. So imagine a dessert that's kind of like a cake / custard, but there's raisins suspended ever so often. That's scattered around. So he's got the positives and the negative charges scattered all over the place. That is J.J. Thomson. Same period, radioactivity is discovered. The discoverer of radioactivity is Henri Becquerel, friend of the Curies, of Madame Curie and Pierre Curie. And Madame Curie, remember Mania, who changed her name to Marie and married Pierre? Remember that? She coined the term radioactivity. They were not the original discoverers, but they worked very closely with Henri Becquerel, who actually did discover it. And they studied it, they described it, and they coined the phrase radioactivity. They defined radioactivity, it's a nuclear decay. It is a nuclear decay. Some elements are naturally radioactive. Uranium is like that. It's element number 92. Look at that. Numero 92, uranium, number 92. Madame Curie went on to discover 2 elements on their own, and they did it with their bare hands, with shovels in the back of an institute, in a shack, in the open, with buckets. That's an alpha particle. A beta particle is negatively charged. It's a stream of electrons. Beta particles are electrons. Gamma radiation is electromagnetic. It is EM radiation, very high energy EM radiation, gamma radiation. The stuff that they use in sci-fi and comics to produce superheroes or mutants or monsters. Gamma radiation, very scary. And we'll talk about that in a second. Is there fine so far? Are you okay? Good. Yep, helium nucleus. Helium. And these electrons, by the way, these electrons, beta radiation. These electrons come from the nucleus. And that's unusual. Why? Because I thought that the electrons were not in the nucleus. I thought the electrons were around. Yeah, that's right. Beta radiation happens when particles inside the nucleus fall apart and produce a stream of electrons that get thrown out of the nucleus of the element. So you know that something is major going wrong there. This is decay, nuclear decay. This type of decay is very common for the large elements, and it starts almost right away. First of all, let me say that radioactivity is extremely natural. Radioactivity is a natural phenomenon. It is not made in labs. It is not scary, except in high concentrations. It is a natural phenomenon partly responsible for our planet to stay warm. The reason we can exist on this planet is partly because of the temperature. And a huge part of the temperature is that the core of our planet is got radiation going on. So it's actually a very natural phenomenon. If I had a Geiger counter here, I could walk it out to almost any construction, any rock. This is, some of these things have concrete block behind them, not the rubber, but the concrete block behind it, and I can measure it, and there's a very slight baseline level of radioactivity, and it is absolutely normal. High levels of radioactivity are deadly, but that's a high level of radioactivity, and that stuff is measured. You can look it up. They're called permissible exposure levels. Permissible levels of exposure or permissible exposure levels. And they will tell you, you can be exposed to this much radiation and still be okay. Meaning, you've had x-rays for your teeth, right? You've had x-rays for broken bones, right? Then, what's the problem? The problem is that you get it for just a few seconds, so you can stay there, but what does the person do, the technician? They leave, don't they? Because that's their job. So over a period of a day, their exposure would be a lot higher than any single patient. So of course, they have to take the greatest precautions because they work in there all day. I personally work with beta emitters, not alpha emitters, but beta emitters. When I was pregnant, both times, and I can assure you, neither one of my children have a second head yet. Well, they're in their 20s. I think it would have come out by now, right? So I think they're fine. And it's all about safety protocols. It's all about safety protocols. Now, having said that, I know myself, and you gotta work, you know, to your limitations. You cannot pay me enough to work with gamma emitters. There is just no way that I would ever personally work with gamma emitters because I'm just not naturally careful that way. And I'd be the one that you see with them naked scrubbing in the shower with the people in the hazmat suits, that'd be me in the middle of the street with a big tent around me. Those are huge safety protocols that have to be very, very carefully followed. And so, in level of scariness, least scary, medium scary, extremely scary. So, what does that mean? It means that if you had a piece of tissue, you can pretty much stop alpha radiation with a tissue. It means anything. Your clothing will protect you. Lab coats and such. But you know, beta emitters are going to hit it and come out. Beta emitters are going to go right through a tissue paper, right through your clothing, so you have to wear latex protection. Gamma? Good luck with that. So, beta emitters. Well, with beta emitters, you need a little bit of a shield. So, a shield, say plexiglass. A plexiglass shield. Latex. A little sturdier, something a little sturdier, will stop beta radiation. Gamma? Good luck, because that'll go straight through. To stop gamma radiation, you're going to need a barrier made of lead or concrete. A barrier of lead or concrete. Gamma radiation.
They use water too. Isn't that what you use in nuclear reactors?
No, the water doesn't come in contact with radioactivity. Please don't think that. The water from a nuclear reactor is a cooling system. What happens in the core, what happens in the cooling system, the water that you hear about is outside. And the water is used to go in and the water goes out. It sometimes, I hate to scare you, sometimes it goes out to a lake.
Oh, I know that.
But then there's a perverse twist of fate. It's not radioactive, it's just warm. Because you just used it to cool something. Fine. A couple of degrees, right? Okay, that's fine. But you know, the little fishies that are normally swimming in that lake have a certain temperature at which their metabolism works, right? Okay. Raise the temperature, the dissolved oxygen is less soluble, so you start eliminating oxygen from the water. So now you raise the temperature for the little fishies, increasing their metabolism, needing more oxygen. But wait, the same temperature eliminated the oxygen, so now they're working faster at a higher temperature, but you're choking them because there's no oxygen. unintended consequences. You think it's okay, and all kinds of things could go wrong anyway. Unintended consequences. So the cooling water is not in contact with the radioactivity. They don't pump that out at all. No. So in terms of scariness, alpha radiation, you can stop it basically with a tissue. Beta, you need harder clothing, plexiglass. Gamma, concrete and lead walls. Right? Okay, so I have a homework for you and you can tell me by Friday. I am going to give you mentally, just in theory, hypothetically, 3 cookies. An alpha cookie, a beta cookie, and a gamma cookie. I'm not hungry, thank you. No, this is the exercise. Save them for when you're hungry, save them for lunch. 3 cookies, alpha, beta, alpha cookie, gamma cookie, and beta cookie. Here's your assignment. You have to hold one, eat one, and put one in your pocket. You have to hold one, eat one, and put one in your pocket. Which one would you do for which? Don't tell me how to think about it. 1913, and the story of Harry Moseley. 1911, thank you. 1911, Rutherford discovers the nucleus. And what's the name of his famous experiment? Gold foil experiment. Gold foil experiment discovers the nucleus. Harry Moseley, by the age of 23, and I already told you the story. By the age of 23, he had done enough work to be deserving of a Nobel Prize. But because of his bravery, some people say, stupidity, some other people will say, he died in World War I. And he cannot get that Nobel Prize. Because Nobel Prizes are not awarded posthumously. You actually have to walk up to Stockholm and go pick it up in person. So therefore, if you make significant contributions but then you die, you don't get that Nobel Prize. Last year they made a huge exception. The last year or the year before with a physics prize, they made a huge exception. The gentleman who won the physics Nobel Prize passed away in the weeks between the ceremony and the award of the Nobel Prize. And so they did give it to him anyway. So I thought that was great of them to do that. So Harry Moseley, I made such a big deal about him. What did he do? Harry Moseley is responsible for the atomic numbers. You think that'd be important. That's what he did. And there's no telling how much more he would have contributed had he lived a little bit longer. This is Harry Moseley's contribution. The atomic number for the elements. He worked with X-ray emissions. He worked on X-ray emissions. He worked with the X-ray emissions of different elements. Remember the story I told you about Dmitry Mendeleev? He said, listen, stop ordering things by weight. You're doing it wrong. And they finally listened to him, right? So they said, listen, people had in the periodic table tellurium in the position of iodine and iodine in the position of tellurium because they weighed in the certain order. So iodine weighs a little bit less, so they put it over here. Tellurium weighs a little bit more, they put it over there. Dmitry Mendeleev said, that's stupid. Tellurium acts like oxygen, selenium, and sulfur. Get it out of there, switch them. I don't know why, he said, right? I don't know why, because he wasn't Harry Moseley 30 years later. But it is. It's going to be this way. Otherwise, it wouldn't make any sense. Because we've got it ordered now by behavior. So all the alkaline metals behave the same. All the alkaline earth metals behave the same. The transition elements show a certain similarity in their reactions. The halogens all work the same. Iodine does not behave like this column. Iodine behaves like this column. So they switched it, and Harry Moseley said, bam, he was right. And this is why. Because in terms of atomic number, tellurium's at 52 and iodine is at 53. And that's why they belong to where they belong. So sometimes you have things that you take for granted. But if you think about who did it in the history and the chronological order in which it happened, it makes a little bit more sense if you think about it, of what happened first, second, and third. Harry Moseley, atomic number. 1922, Bohr's atomic model. Finally, we're starting to get an idea. We're starting to get a better idea of the model of the atom that is absolutely not the plum pudding of 40 years before. No more plum pudding. These folks, starting from starting from roughly J.J. Thomson on down, and with the Curies, there's actual photographs, so you can look these things up. And all the other ones, the ones before, obviously, in the 1700s, before the daguerreotypes, there were no photographs, there were paintings and sketches, so you can see what these guys look like. And Bohr says, Niels Bohr, Danish scientist, says, hey, the nucleus, like Rutherford said, is at the center. It is very, very heavy. It carries the mass of the atom. Of course it does, because we know it contains the protons plus the nucleus, plus the neutrons. And both of those particles are where? In the nucleus of the atom. And I know that because my mass numbers, say for example, if I say that magnesium, say for example, let's say sodium with a 23. 23 is the what? The atomic mass. What is the 11? Atomic number. So the atomic number is which one? The protons or the neutrons? The protons. The protons is the atomic number. The number of protons defines the element. That's the number that Harry Moseley is responsible for. So when you talk about sodium, we talk about an atom that has 11 protons in its nucleus. Any atom that has 11 protons in its nucleus is a sodium atom. Period. End of story. Nothing else matters. Nothing else. Doesn't matter how many electrons, doesn't matter how many neutrons, it's the protons that define the element. So if I tell you that I have an element that has 8 protons in the nucleus, what element is it? Oxygen. No matter how much it weighs, no matter how much it weighs, so the mass of the element is concentrated in its nucleus. Rutherford's experiment, famous conclusion, the atom is mostly empty space. Mostly empty space. And Bohr says, no more plum pudding. There's an order, and this is it. At the center, there's a very heavy nucleus that Rutherford found. The electrons are around in allowed orbits, and we see the little symbol that you will now recognize universally as what we think an atom looks like, and that's wrong too. Okay? In level of wrongness, this is enormously wrong. Hugely, enormously wrong. Even this one is wrong, but is this one better than that one? Slightly, ever so slightly. We good? So 1922, the Bohr model of the atom. No more plum pudding. Protons and neutrons at the center, electrons on the outside. So you have to be able to tell me the protons, neutrons, and electrons of any species that I say, any one. So say for example that I have this one, carbon 14 and 6. This is a nuclide. This is a nuclide symbol. This is a symbol that contains the atomic number. That contains the atomic number, and I know that's the atomic number because it's a smaller value of the two. No matter where they put it on the periodic table, some periodic tables have this backwards. Sometimes they have the number down here and the mass up there. But when you look at the numbers, that's a 91 and that's a 40. The smaller value is always the atomic number, and that's the number of protons in the nucleus. We good? So now, in any element, and say for example that I have oxygen 18 and 8, you should be able to tell me protons, neutrons, and electrons of any species. In fact, let's make that an ion. Protons, neutrons, and electrons of any species. So tell me, how many protons in the carbon that's 14? 6. It's a carbon, so that's a 6. There is no doubt that those are 6 protons. How about neutrons?
8.
Because it's the difference with the mass. And how about electrons?
6.
Because in the neutral element, the protons have to be equal to the electrons, so that's a 6. How about that oxygen? Protons, neutrons, electrons.
8 protons. 10 neutrons.
Protons? Definitely 8, because that's its atomic number. The number of protons in the nucleus defines the identity of the element. How about those neutrons? 10. And how about those electrons?
10 electrons.
10 electrons. Because originally he had how many? 8, but he's got a charge of -2, so he's got 2 more. Is that correct? Okay, perfect. Protons, neutrons, and electrons. Protons, neutrons, and electrons. So the neutron. 1932, a man by the name of Chadwick. And why did it take so long to find neutrons? Because they're neutral. The other ones, I know it sounds stupid, but think about this. The positives and the negatives were attracted to magnetic fields. So they found those particles fairly quickly. But the neutrons took a long time. 1932, he finds the neutrons. And the mass of the atom is complete. The idea of the mass of the atom is complete. So now, the mass number is equal to the protons plus the neutrons. And these are atomic mass units. Atomic mass units. Protons in general are equal to 1 atomic mass unit. Neutrons weigh the same. 1 atomic mass unit. Electrons have what you call no rest mass. If you get technical about it, it's 1/2000 of a AMU. It basically means electrons don't weigh anything. It basically means electrons don't weigh anything. For all intents and purposes. We good? Okay. So the picture of the atom that's emerging. Well, let's talk about those energy levels. And for the sake of argument, I will now repeat the mistake that every chemistry teacher has ever made. And for the sake of being absolutely unimaginative, let's go with the really wrong version of what an atom looks like. By holding just lines and making it look like something it totally isn't, which is like a racetrack with a center. Okay? But I need to do this, and everybody needs to do this, to make the same mistake, because I can't actually draw you what an atom looks like. No one can. No one. An atom is an incredible thing described by quantum mechanics. It had to be invented in 1932. It was invented. Quantum mechanics is a branch of mathematics, a branch of physics that was invented by Schrödinger. By Erwin Schrödinger, and the famous Schrödinger equation. And that had to wait. And why was that necessary? Because classical mechanics, described by Newton, where positive things are attracted to negative things, and things bump into each other, and for every action there's an equal and opposite reaction, and force is equal to mass times acceleration, and everything you ever learned in a physics class, all that collapses at the subatomic level. Nothing behaves the same way once it starts moving at the speed of light. And now, we're in the world of Albert Einstein. Because when things begin to move at the speed of light, the physics appears to change. So you cannot use classical mechanics, the way you describe large bodies, to describe small things moving at the speed of light, which is what we have here. So I can't actually draw you an atom. But I can tell you this, they're in layers. Layers. Atoms have layers. And they're called energy levels. Energy levels. And the symbol, big fan of Shrek. Energy levels. They are called principal quantum numbers. Principal quantum numbers. Smaller letter, lowercase n. Lowercase n. Those are energy levels. And this is called a principal quantum number. Principal quantum numbers go from 1 to infinity. There's no 0. It goes from 1 to infinity. So principal quantum number 1, 2, 3, 4, 5, 6, and on and on and on. We good? Those are principal quantum numbers. Those are the organizational levels, main energy levels, where atoms keep their electrons. In other words, this craziness of all the electrons orbiting around a nucleus that I can't draw because no one can, that stuff actually has an order to that madness. And the electrons are not just thrown around, they actually have an order to them. And you know what that order is. What is it? 1s, 2s, 2p, 3s, 3p, 3d, 4s, right? That's the order. And this is your first number. In the first level, there's only one type of orbital, an s. In the second level, there's s's and there's d's. In the third level, there's s's, p's, and d's. And for the first time, in the fourth level, s, p, d, and f. Those letters stand for sharp, principal, diffuse, and fundamental. Sharp, principal, diffuse, and fundamental. And you can keep it going. You can keep it going. S, P, D, F, G. S, P, D, F, G, H. Never heard of it. But you know what? We're ready. The organization of the atom is already set up. It's called the Aufbau principle. The order that you described, 1s, 2s, and all that, it's called the Aufbau principle. It's already set up. So as soon as we find bigger atoms, and we know that we have to keep going with this list, shoot, we left the blanks. And we can start another row as soon as you want. As soon as people start finding one, you can find one, you can start a new row. We don't have one yet, but we're ready to go. If you ever needed to keep more electrons, we're ready. The thing is that our natural limit of stuff that we found / made in labs takes me as far as what quantum number? 7. That's about it. This is what I got. I'm only up to here. But not all the way down to levels G and H. I don't have those filled up. This is as far as my periodic table goes. Like a house that has 100 rooms. You might be occupying 40, but you know you can get more people. Like a house with empty rooms. We're ready to put the electrons in. Is that okay? Okay, perfect. Diffusion. Sharp principle, diffuse and fundamental. Everybody fine? So far so good? Okay. The 1930s. The 1930s also has the discovery of nuclear fission. What is that? The discovery of nuclear fission. What is nuclear fission? The splitting, because the putting together is called what? Fusion, that's the other one. So the one we can do is nuclear fission. Okay? Nuclear fission. And what example do we have of nuclear fission? Right? Atomic bombs and mushroom clouds. Is that correct? Right. So as soon as humanity discovers metals, it sharpens them and uses them to do what? To stab the people that are pissing upstream, to take their stuff and their women and their children. So as soon as you discover something slightly better than a sharpened spear, what do? Well, now I have a question for you. Last time I asked you, you guys are the new generation, I'm going to be old and you guys are going to be in charge of the world. I want it to be a good one, because I'll be defenseless and all that. So, no, seriously, right? So I asked you, so governments should only let some people fight their wars then, and I guess you decided that it needed to be the stupid poor people. Is that what I heard? Because I asked you, should the smart ones be kept out of wars, and you said, yes, keep the smart ones out of war. Okay, just checking. Think about it. So I have a new question for you. This guy, that guy, this one, was a really nice guy. He believed in the 1930s, in the early 1930s, that scientific information should flow. That science was separate and pure from anything else in the world, and that no single person should withhold information. That every human on this planet has the right to know all scientific information. What do you mean no? Because who in the 1930s really would have liked to have known before we did about nuclear fusion? The Germans. And they were having a rally on their own because the Nazis were in power. And they were in danger of the Nazis figuring things out. They almost did. Albert Einstein had to write a letter urging the American government to hurry up and fund the projects because the Germans were about to discover it. And Niels Bohr says, oh, no, but science is pure. And everyone should know. This material should be presented to the whole world. And the United States government said, shut him up, or we're going to throw him in a hole for the duration of this war, and he's not gonna see daylight for the next 10 years. So he finally saw things in the way that was more helpful, and all the scientists in Nazi-controlled countries, like Enrico Fermi in Italy, who was told, hey, you want a Nobel Prize, we want you to go up there at Stockholm, we want you to wear this uniform and go over there and salute the Nazi party when you get the award. And he said, okay. And he closed the door. He said, honey, pack, we're leaving. You know what they did with the Nobel Prizes? They melted them. They dissolved the gold before giving the medals to the Nazis. They dissolved the gold and kept it in a bottle. And when they got out, they reprecipitated the gold back out and reformed the medals, just to screw with them and not let them have the gold medals. Yeah, you can do that. You can precipitate gold, you can dissolve gold and precipitate it back out, just out of spite. That's an incredibly dirty vengeance, don't you think? Ultimate geek vengeance. So yeah, I'm gonna dissolve this gold right now. We got very lucky that we ended up with a better scientist. Otherwise, who knows what would have happened. So, the discoverer of nuclear fission, the element that is devoted to that person is element 109. And the person's name was Meitner. Meitner, a German physicist. Can you guess? Just guess real quick. Just guess real quick. Meitner's first name. Bohr's was Niels Bohr, and Bohr has his own element. And you won't believe me, but it's true that the IUPAC, the people who put the names on the symbols of the atomic symbols for the table, they discussed these things, and they had a fight, and they wanted to call it Niels Bohrium or just Bohrium, but they said Bohrium sounds like like boring, right? So God forbid somebody find chemistry boring, right? So because that would really put them over the edge. So the huge fight was, should the element called Bohrium or Niels Bohrium? So they went with Bohrium because Niels Bohrium was too long. So this element 109 is Meitnerium. So real quick, Meitner's first name, German scientist, German physicist in the 1930s. Hans, no. I usually get Adolf. But we're running out of time. No more guesses? Hans? How about Lisa? Shame on you, every single one of you ladies. None of you, I heard somebody say it might be a girl. None of you guys thought to guess a girl's name, huh? Her name was Lisa Meitner. Lisa Meitner. The discoverer of nuclear fission. Incredible story. She was a German physicist, a female German physicist. And if you think it's bad to be a female physicist, try this. Being a female German physicist in Nazi Germany. When things got really bad, her co-workers smuggled her out of the country. In like you see in the movies, like spy stuff, and they took her to Scandinavia to hide her. And they had secret communiques by paper, you know, nothing you have to try to remove yourself from the world you live in. And try to imagine secret documents being passed back to the lab in Germany. Because the German scientists that were working with her risked their lives. If they admitted that they were working with a Jewish scientist, they would have all been executed. And they kept working together. The people in Germany, the two guys in Germany that worked with her their entire lives together, published the paper without her. They were in a hurry, and they felt pressure, and they had to do it so that they could get the credit first and end up with Nobel Prizes. But her name wasn't on it. They couldn't, and they couldn't put her name on it. It would have meant that they would have executed them. But they had to publish it first. And she totally understood that. She was okay with it. And she's fine with it. They lived a very, very long life. They were friends until the end in their 80s. And as long as humans are walking around this planet, everybody's going to know that story. Because if you look up what the elements mean, inevitably, remember, your name on the periodic table is forever. Forever. As long as humans have reason and we walk on this planet, that's never going to go away. So, element 109. Some of the other ones, Rutherford, element 104, this one, Rutherford. Minor, Einstein, where's ES? Einsteinium, this one. Berkelium, Curie, Americium for America, Fermium for Enrico Fermi, Nobel, Lawrence, Mendeleev. This is Mendelevium for Dmitry Mendeleev, element number 101. So you can look them up. Something was becoming extremely obvious. That the physics that we knew from Newton was absolutely wrong and just not possible.
And what's the story with California?
California, when you own an accelerator, a nuclear accelerator, you get to name your element. If you discover one and it's confirmed, you get to name it. So people name it. If you work at Berkeley, maybe you want to call one Berkelium after Berkeley, after the University of Berkeley. And California, because Berkeley was already taken, and it's already in California, so they said, you know, there's a lot of labs here, California. Einsteinium, yep. Polonium, the one that Madame Curie, that Madame Curie discovered. They named it this one, polonium, after her native Poland, because Mania Skłodowska was Polish. She lived her life as a French woman. Most of her life was lived as a French woman, but she never forgot that she really was from Poland. So, electromagnetic radiation. Electromagnetic radiation. Light. Light behaves as a particle called a photon. The particles of light are called photons. Light also behaves as a wave. And that fact is called the wave-particle duality of light. The wave-particle duality of light. If you set up an experiment to prove that light is a wave, light behaves as a wave, and you can do diffraction. It's a property of wave. If you want to set up an experiment to prove that light is made up of packets of photons, light will behave as a photon. It's almost as if light knew what you were testing. This one, the wave-particle duality of light, and this one. Both of those things were from the 19th and 20th century, early 20th century. This one, mostly Einstein. Mostly Einstein. Let's talk about electromagnetic radiation. Electromagnetic radiation. Light. In 1045, we're going to be focusing on the wave behavior of light rather than the photon or the particle behavior of light. So tell me, what is the electromagnetic spectrum? What's the electromagnetic spectrum?
Different wavelengths of light, different wavelengths.
The colors is part of it, right? So the EM spectrum is a list of wavelengths and frequencies. Wavelengths, frequencies, and energy. I want to put the word high and low, and you tell me roughly where things belong. Ready? Microwaves. Low. Radio.
Low.
The color blue. I would say low, right? Because I'm not particularly affected by the color blue. I'm just saying. Just saying. So somewhere in here is the visible spectrum. And that breaks down into Roy G. Biv. But if I want to spell Roy G. Biv, tell me, where does the R go and where does the V go? Does the R go towards the high or the low?
Red goes towards
It's
The
goes to
red.
the low.
The red. Is it a high or a low?
the
Low.
left side, it's the long
Low.
wavelength.
We good? Okay. On this third rock from the sun, we have developed into creatures who have an EM radiation detectors right in here, right behind this area. They're wired. The EM radiation goes through a hole roughly in this area, some better than others. Information gets transmitted into a central processing unit right up here through nerve endings and stuff that's all connected that's in here. So when you grow up, in every language where you grow, whatever language you grew up with, someone taught you a word for this. You know, you can take a child and you can tell that child that this is called green. You know that's just a word, right? And that child is going to forever call this color green. That's just a word. Because the reality is that you are perceiving a certain color of electromagnetic radiation. Is that correct? So, just over the violet, there's the ultraviolet. And just under the red, there's what? The infrared. Just under the red is the infrared. Is that correct? Okay. So, at what point in the electromagnetic spectrum would I expect to find X-rays? Ah, now we're talking high, right? X-rays. Ionizing radiation that you can only be exposed to a certain permissible level of exposure, only so much, because if you're exposed to large amounts of ionizing radiation of very high energy, your bag, the one that contains all your gushy parts, is going to be affected. Why? Because that radiation, starting from ultraviolet, starting from this point right here, it begins to affect the bonds that make up the matter that covers your skin. And if that radiation starts affecting the cellular growth, what do you call it? Skin cancer, melanoma. And that starts happening right here, right there. You know that because at this point, you start buying products to protect yourself. Sunscreen. Nobody walks around going, oh my God, I think there's FM in here. Well, they might. I mean, you know individuals that might be that way. But for the most part, they're not actually receiving FM, right? No, say no. Say no. How about AM? Can they receive AM? No. How about if they wear braces? Then can they receive it? No. No. Of course not. To receive anything that's outside of Roy G. Biv, all of us, top dwellers of this third rock from the sun, require an instrument. So no, you're not going to receive microwaves unless you have a telephone or some communication device. No, you cannot receive ultraviolet. No, you cannot receive radio or IR. You can be exposed to it, but you're not going to be interpreting anything outside of Roy G. Biv. We good? Okay. So finally, somewhere over here, there is the worst form of radioactivity, which is gamma radiation. And that's out here. Gamma rays. That type of radiation will turn you into a crispy critter inside of 3 days. Exposure to gamma radiation is incurable. Your organs will liquefy, and you will die, and there is no cure. And those people are called the walking dead after exposure, because you're going to be walking around for a certain period of time, but your organs will slowly liquefy. Do you know what Chernobyl was? That's not Cher's full name, by the way. It's not. It's Cher. So Chernobyl is a city. Where? In Russia. Right. Near Kiev. Right. And what happened there? A nuclear reactor had an accident in 1984 or so. And if you look up the blow by blow, the timeline of what happened first, second, or third, it is scary and alarming how they reacted and the mistakes that were made. They actually had a meltdown. Every satellite on the planet picked up a hole on the ground And back then, we weren't as open with the Russians weren't that open with us. And all of Europe could tell that there's a piece missing in the city. And they're like, no problem here. Dude, you have a hole in the ground, we can see it. Remember the spy satellites? We can see it. No problem, everything under control. So a radioactive cloud waves over Europe. And Europeans are going, Russia, not funny. Not funny at all. Especially when they denied it for some time.
Didn't Switzerland
So-
detect it first?
I have no idea who detected it first. No clue. I have no idea who detected it first. The pilots who surveyed the area, the Russian pilots who surveyed the area, got into the planes knowing that that's the last time they were boarding those planes. And they did it anyway. They had to. So sometimes these things happen, and there are individuals in charge who have certain jobs that are really amazing. And those guys did it anyway. They knew about exposure levels, and they knew that after they came back, they had basically 3 days to live. They did it anyway. Waves exist 2 to 3 days. What, do you decay? I mean, I don't know what the progress of the thing is, but you begin to show symptoms of this first, and then after this hour, until. Alright, over here. Waves. Here we go. Energy, frequency, and wavelength. Energy is equal to H times the frequency. H is a constant. It's Planck's constant. 6.63 times 10 to the minus 34 joules second. That's the value of H. And it's the same number, 6.63 times 10 to the minus 27 erg second. And this is not per. I want to call your attention to the fact that that's a multiplication dot. Joule second or ergs second. I'm saying this word. Ergs. An erg is a unit of energy, like a joule or a calorie. It is a very tiny unit of energy. 1 erg is the amount a fly uses to do a push-up. A fly. That's 1 erg. Flies do push-ups. They measured it. The electrode. Drop it, give me 20. Run! No. They use that imagery, they use that mental imagery to simply show that an erg is a very small unit of energy. I didn't make that up, I actually got that from you. A fly doing a push-up, 1 erg. Here's I swear to God, I swear. Okay, so this is 2 numbers you have to know. Just like the ideal gas constant, you have to know this one. This is H, Planck's constant. That symbol is the frequency. That symbol is its frequency. And frequencies are in seconds to the minus 1, or cycles per second. Otherwise known as hertz. Hertz. Cycles per second. Those are the units of frequency. Here's my impression of a wave. Here's my impression of a wave that does not scare me. Nice big floppy wave. Nice big wavelength. Not too many of those humpy guys per unit time. This is good. This is radio, microwave. This is good. Here is my impression of a wave that terrifies me. Extremely high energy, extremely short wavelengths, extremely high frequency. This is the one that turns you into a crispy critter inside of 3 days. Okay? So, directly proportional, inversely proportional. High energy waves have high frequency or low frequency? High frequency. And wavelength? Inversely proportional. Right? So all the algebra that has to do with E equals H nu, you're responsible for it. What's new? C over lambda. Two physicists are walking down the hallway, one says to each other, hey, what's new? And the other says, well, C over lambda, of course. I'm sorry. What's new? C over lambda, of course. You know I'm being very silly, but hopefully you'll remember. What's new? C over lambda. This is a wavelength. And that is the speed of light. 3 times 10 to the 10 centimeters per second, or 3 times 10 to the 8 meters per second. Okay? Energy, frequency, and wavelength of a radiation. Energy, frequency, and wavelength of EM radiation. Alright? Alright, so you guys are fine.
It says 3 times 10 to the 10.
3 times 10 to the 10 centimeters per second, and 3 times 10 to the 8 meters